as introduction of Fourier series, periodic functions, general formulation of Fourier series, Euler's formula, and examples based on above topics. So let us understand very first what are sequences. So the basic definition of sequence is a sequence is a function whose domain is the set of all natural numbers, whereas the range may be any set S. In other words, a sequence in a set S is a rule which assigns to each natural number a unique element of S. So that is called a sequence. A real sequence is a function whose domain is the set of n natural numbers and the range is a subset of all set of real numbers. So basically we can write like this. A function which is set from natural number to the real number set, or we can define like this also as x such that from natural numbers to the set of real numbers, and it is called as real sequence. Range of a sequence. The set of all distinct terms of a sequence is called its range. So you can note down a point that it's for you to remember for you people. In a sequence xn, since n belongs to n, where n is an infinite set, the number of terms of a sequence is always infinite. You already know about this. So for example, if xn is taken as -1 raised to the power n, that means if as we substitute the values of the small n, this sequence in curly bracket can be mentioned in the form of a set which is having the elements as -1. When this n is equal to 1, this becomes -1. When n is equal to 2, this becomes +1. And similarly, we keep on substituting the values of small n. We keep on getting the elements of this sequence n. So in this way, we can define the range of this sequence as -1 to +1. How can we say this? Because we are having the elements either -1 or +1. So we can define the range of the sequence as -1 to +1, which is a finite set. Alright, and which is of course a subset of real numbers set, capital R. Constant sequence. A sequence xn defined by xn is equal to c, where c is any constant obviously belonging to the real number set for all small n belonging to capital N is called a constant sequence. So of course we can write a number of times this constant, which is a constant sequence, like here. So we can also define the range of the sequence as this constant number itself. Understood? So now bounded and unbounded sequences. What are bounded sequences? So let us understand first above bounded sequence. So a sequence an is said to be bounded above if there exists a real number k which will never be 0, such that this an less than equal to k for all n belonging to natural number set. Right? So this an is what? The journal element of the sequence, and sequence is mentioned in the curly bracket. So if this condition holds, then we say that we have bounded above sequence. Alright. So similarly, we can show bounded below sequence if a sequence is following the condition like this: an greater than equal to a constant k for all n belonging to natural number set, then the sequence is said to be bounded below if there exists a real number k such that this condition holds. Right? Okay. So bounded sequence, bounded only word is used when the sequence is upper and lower. Both the bounds exist. A sequence is said to be bounded when it is bounded both above and below, as I have already told you. So a sequence is bounded. There exist two real numbers, k1 and k2, or small k and capital K. Of course, small k will be less than or equal to capital K, such that this condition holds. Or in other words, you must have heard about if any function is bounded, then we write like this, mod of this. Then what we call it, function fx is lying between minus m2 plus m. So the same condition holds for the bounded sequence. Unbounded sequence, when a sequence has no lower limit or upper limit, then that is called unbounded sequence. That means if there exists no real number m such that mod of an is less than or equal to m for all n belonging to natural number set, then the sequence an is said to be unbounded. Alright, so if no real number exists like this. Let's have an example. Consider the sequence defined by an is equal to 1 by n. Right. So if we write the sequence in this curly bracket, so this becomes, we'll take the values of small n from where? From natural number set. So we substitute, we keep on substituting, n is equal to 1, 2, 3 and so on. So you can see that the first element is 1 by 1, that is 1, and so on. If we move to n tends to infinity, then what will happen? It will become 1 by infinity, that tends to 0. So that means its minimum value is 0 and maximum value is 1. So that's why the sequence lies between 0 to 1 for all n belonging to natural number set. That means we can say that this n is bounded. Now we can have another example where the sequence is defined by 2 raised to the power n minus 1. So we can substitute here the natural numbers like n is equal to 1, 2, 3 and so on. So we are getting these terms in this sequence. Alright, so if small n tends to infinity, what will happen? This 2 raised to the power infinity, which of course will tend to infinity, means upper bound does not exist, right? So here lower bound means lower limit is what? 1. So it is what? A bounded, lower bounded. Its lower limit exists. That means lower bound exists, but it is unbounded above, right? Because it was tending to infinity. So there was unbounded sequence, which is above unbounded sequence, right? Next, convergent sequence. So a sequence is said to be convergent if its limit is finite. For example, if we have this sequence 1 by 2, 1 by 2 square, 2 cube and so on, 1 by 2 raised to the power n. So of course, if n tends to infinity, the denominator becomes infinity and the whole value becomes 0, which is of course finite. So we call that the sequence is convergent. On the contrary, divergent sequence. A sequence is said to be divergent if this limit is not finite. That means if we take limit n tends to infinity, the sequence is having the value either positive infinity or negative infinity. Of course, it will not have, it will tend to either positive infinity or negative infinity. And that sequence is said to be divergent sequence. So, for example, if we consider this as a sequence, and here if n tends to infinity, this sequence is going to have the value as infinite. So, in this way we can say that this sequence is divergent. Another example we can take this sequence minus 2 raised to the power n, and here if we take n tends to infinity, the value of this sequence becomes minus infinite. So in this way we can call that the sequence is divergent. Oscillatory sequence. If the sequence is neither convergent or nor divergent, then it is called an oscillatory sequence, right? And oscillatory sequences are of two types. For example, minus 1 raised to the power n we have. Right. So it's a bounded sequence. Why? Why? Because its lower and upper limit exists. Let's see. Limit n tends to infinity a to n. A to n means minus 1 raised to the power 2 and whole power n. So it is what? Minus 1 square is plus 1, and that's power n gives us 1, right? And here limit n tends to infinity. If I take n odd, that means if I take 2n plus 1, then I'll have here minus 1 into plus 1, that will give me minus 1. So in this way, if n varies, we are having two different values, right? So in this way, we can say that this is an example of oscillatory sequence. I hope it's clear. Next is monotonic sequence. A sequence is said to be monotonically increasing if its successive terms are greater than or equal to its previous term, right? So here we can mention in journal like an plus 1 is greater than or equal to an for all n belonging to natural number set, capital N. So we can write like this in expanded form, a1 is less than or equal to a2 less than or equal to a3 and so on. So this is an example of monotonically increasing sequence. On the same side, we can write for the monotonically decreasing sequence, like its successive terms are of course less than or equal to its previous term. So we can write in this manner for monotonically decreasing sequences. Third is, a sequence is said to be monotonic if it is either monotonically increasing or monotonically decreasing. If any one condition is holding good, then we can say that sequence is monotonic. A sequence is said to be strictly monotonically increasing if no equality sign is there. Means we have to focus on this. Means it is strictly greater than the previous term. Means successive terms are strictly greater than its previous term. A sequence is said to be strictly monotonically decreasing if its successive term is strictly less than its previous term. A sequence is said to be strictly monotonic if it is either strictly monotonically increasing or strictly monotonically decreasing. Limit of a sequence. So you must have already aware about this definition, which we have so many times used to define for the limit of any function to exist. So here's on the same pattern, a sequence is said to approach the limit small l, of course that is finite, when n tends to infinity if for each epsilon positive there exists a positive integer m such that mod of an minus l less than epsilon. Of course, this epsilon is very small for all n greater than equal to m. So this is mathematical definition, and this definition is that which we use in our questions. Alright, this is mathematical definition, basic definition, and this we use in our questions. So in symbolic form, we can write like this. Limit n tends to infinity, an is some finite value. So next is, every convergent sequence is bounded. Of course, because convergence definition is what? The sequence converges to a finite limit. That means converges means like this. Like in physics, we have that a ray is convergent. On the same pattern, we can say that we have a sequence as n tends to infinity. The value of that sequence is finite. So if it is finite, that will be known as the boundedness of the convergent sequence. Let k and capital K be the least and the greatest values of the sequence. So of course we can define the boundedness of the sequence. So we can say that every convergent sequence is bounded. right? Let's have an example of monotonic increasing sequence which is convergent and the second part is divergent. So let's have a sequence, an example of 1 by 2, 2 by 3, 3 by 4. You can notice the pattern of the sequence. The numerators are getting on increasing and similarly denominators are getting increasing by the amount 1 which is being added to the numerator successively. So in this way we can write the nth term of the sequence as n by n plus 1. So this is nth term of this sequence. So you can calculate the terms. This is 0.5, this is 2 by 3 which is greater than of course 0.5, 3 by 4 is of course greater than 2 by 3 and 0.5 and so on. So we can calculate the numerical values and call that the sequence is strictly monotonic increasing. So here we can calculate the value of the sequence whether it is convergent or not. So here an is n by n plus 1. So if we take the limit n tends to infinity an, we'll simplify it and of course this term vanishes and we have 1 as the result. So 1 is finite, so we can say that monotone is strictly monotonically increasing sequence is convergent here. Right, so in this way we can show here. Second part, we can have an example of monotonically increasing sequence, strictly monotonically increasing sequence, but it diverges. So consider an example of this 1, 2, 3 up to n, and of course all the terms are strictly greater than its previous term. So we can say that the sequence is monotonically increasing, and if we take the limit n tends to infinity, our value is tending to infinity. Alright, so in this way we can say that the sequence diverges to plus infinity. Now let's have some more examples. Discuss the convergence of the sequence an, where first part is the second and third. So we'll solve these three parts one by one. First is an is equal to n plus 1 by n. So we'll check whether the sequence converges or not. So here we'll simplify that whether its next coming term or successive term is greater than the nth term or less than. So we'll check here. So here I have taken an plus 1. So if n is replaced by n plus 1, then this becomes n plus 2 by n plus 1, and I subtract the nth term here, then I'm getting this value. So of course which is less than 0. So here we can write that an plus 1 is less than, strictly less than an. When successive term is less than the previous term, so we can call that the sequence is decreasing strictly, right? And of course this n, if we calculate when n tends to infinity, this value is 1 and this value is less than 0, means of course it is lesser than its previous term. So this series, the sequence is bounded below by 1, and since it is decreasing sequence, so it is bounded below, and of course it will be convergent then. Next part, an is equal to n by n square plus 1. So we'll follow the same pattern that we'll take the difference of successive term with the previous term, and here of course n is replaced by n plus 1 to get the next term, and substituted the values. After simplifying, I'm getting this as less than 0 for all small n belonging to capital N. You can substitute here and check it. So here we are getting next term which is less than the previous term. So we can say that the sequence is decreasing, and of course it's bounded below by the amount 0. After simplifying this, by taking the limit n tends to infinity. Of course, we have already studied this. So its lower limit, lower bound exists, so it is bounded below. Of course, it will be convergent. So here we can check its lower bound after substituting, as I have already told you here in this step, that its value is 0. Third part, so here we can have that we can have a look at this example that it is a GP, and if we find its n plus 1th term, sum of n plus 1 terms. So using this formula which you have already studied in 12th class, we are getting this value here. So if we substitute here n tends to infinity, if we take the limit as n tends to infinity, then I am getting the value, of course, this is n plus 1th term, an plus 1 minus an. If I do, then I am getting this, and this will be, if we substitute small n belonging to natural number set, then of course we'll be having some positive values, right? So here we can say that successive term is greater than its previous term. So it's an example of increasing sequence. And it is bounded above by the amount 3 by 2. How? Because if we take n tends to infinity, this term becomes 0, because 1 by 3 raised to the power infinity becomes infinity, so 1 by infinity becomes 0. So in this way we have bounded upper, means upper limit as, or upper bound as 3 by 2. So in this way we can say that it is convergent. Alright. Infinite series is, if sequence un is a sequence of real numbers, then the expression u1 plus u2 plus u3 plus and so on un. That means the sum of the terms of the sequence which are infinite in number is called an infinite series. So initially we had completed finite series which was having n terms, and here we are having the terms tending to infinity. Right, so usually these infinite series are denoted by using the symbol as summation from n is equal to 1 to infinity.